In this video, we'll be looking at the binomial theorem. So, first of all, I'm just going to expand some brackets. Let's just look at generally a plus x. Sorry about that. A plus x to the n. All right. So n equals 1. All right. That one's fairly obvious. That's a plus x. All right. N equals 2. I might just like to draw a line there. So a plus x squared, which equals a plus x, divided by a plus x, okay, which is a squared plus 2ax plus x squared. Alright, n equals 3. This is going to be interesting. So that's a plus x to the power of 3, which equals, so we got, it's actually squared, a plus x squared divided by a plus x, and we have our result here, so let's use that, and that is, well, let's just do the algebra, let's find out. So that can be a cubed plus 2a squared x x squared a plus a squared x plus 2ax squared plus x cubed, which equals, so let's collect the like terms, a squared x, there you go, and then there's the other two, the x squareds in there, so that's a cubed plus 3a squared x plus 3ax squared plus x cubed. Alright, okay, so from binomial expansion we found that expanding brackets is a quite a long-winded process really, but actually I'd like to introduce you to something called Pascal's triangle, and what that is where the elements on the edge are all ones actually, and the elements here in these places are the product, well not the product but the sum of the ones that are above. So there you can see 1, okay, there's nothing to do there, but 2 goes down, so 1 plus 1 is 2, and here, so let's just, this one's 3 in between 1 and 2, and then this one's 3 in between 1 and 2, and there's another, and this process carries on. And you see it's natural numbers this way basically, because you know 1 plus etc. 5, 10, 10, 5. Alright, and then that process carries on. Now, let's go back to a plus x to the n. When n equals 3, the product there was a cubed plus 3a squared x plus 3ax squared plus x cubed, right, and n equals 4, that's a to the power of 4 plus 4a cubed x plus 6a squared x squared plus 4ax cubed plus x to the power of 4. Now, you may have noticed now, look at that, there's 3 here, and this is actually technically a 1 here, there's 1s here, so these match, and here, 1, alright, 4, 6, 4. Oh, so it seems like there's quite a relationship between this, or binomial expansion, Pascal's triangle. Also you notice that the first one, well it depends which order you put it in, but if you do it in basically one can get it in a descending order in A, and then it's an ascending order for X. So as one decreases, one goes up by the same rate, which is quite an interesting thing. Also, there is some notation to go with this. NCR notation. N choose a number, place along. So, for a to the power of x, a plus x to the power of n, when n equals a certain number, let's say for example 3, so if n is 3, and then the r is the rth place along that area. So, however, it starts actually, it doesn't go, sorry, I must have accidentally, it goes from 0 to 1, and then 2, and then 3. So you can't have a fourth place in there. If that makes sense. So it starts at 0. So n choose 0. Okay, so let's give this an example. Let's choose 0 again. So 3 choose 0 equals 1, and then 3 choose 1 equals 3, and you see it goes along, and then 3 choose 2 equals 3, and then 3 choose 3 equals 1. Okay, so you could put this generally, I guess. Some nice general things you can say. N choose 1 equals n, n choose 0 equals 1, and n choose n equals 0. Oh, sorry, 1. Let's just pretend that never happened there. Okay, so there we go. From this, we can see that the binomial theorem is quite a useful tool. And there are quite a few things you can do with it. It has some nice applications, especially with larger multiplications and expansions and things. For example, actually another application is actually estimating values. So try and do 0.98 to the power of 5 out, like, just randomly or in your head or something. Good luck with that. With binomial expansion, it's actually made quite nice, because you can imagine this 0.98, for example. Let x be 0.01, and then you can minus 2x to the power of 5. So you see, so 1 minus 2, minus 0.1 equals 0.98 to the power of 5, and then you can use some expansion. So let's do that. Which equals 1 plus, so minus 2 to the power of x is and then this one is, so that's 1 to the power of 5, let's imagine. This is 1 to the power of 4 times by minus 2x plus, oh, but this is also 5, of course, and then this is 5 choose 2, so that's 5 choose 1, which is 5. 5 choose 2 times by 1 to the power of 3 minus 2x squared plus 1 to the power of 5 choose 3, not written very well actually, it's meant to be a bit smaller, it's meant to be superscript. 5 choose 3 divided by 1 squared minus 2. First of all, I'm not going to do the calculation just yet. I'm going to simplify the algebra and then I'll do the calculation. So x to the power of 3 plus 5 choose 4, that's 5 choose 0 by the way, times by 1 to the power of 1 minus 2x to the power of 4 plus 5 choose 5, which is 1, times by 1 to the power of 0, which is 1, times by plus, oh no, sorry, times by minus 2x to the power of 5, which equals, so that's minus 10x. Oh, sorry, 1 plus. Okay, I'll just get the rubber out. Not best. Okay, alright, g equals 1 minus 10x plus, I'd have to get the calculator out. Not sure what 5 to shoot, that was 10 actually, I know that, but so that's minus 40. Oh no, that's plus 40 x squared plus 5. This is riveting commentary, I know. Apologise. So that's also 10. That's minus 80x cubed. That's 5 as well, isn't it? Let's just check. But I'm pretty darn sure it's, yes, 5. 5 25. 16. That's also 80. And then minus 32x to the power of 5. Okay, so that is approximately 0.9039.